Section 28.6, the equivalence of mass and energy. So, the total energy of an object we can describe with mc squared. We're now getting into Einstein's famous equation. We'll get to that more in just a moment, but we'll need to divide it by this square root term of 1 minus speed squared divided by c squared. Where as this is going faster and faster, the object's going to have more and more energy. This is the assumption that every object has energy just by having mass. So this is known as the rest energy of an object. We have an E sub 0 to say this is just the default minimum energy, that even if you aren't moving, if your speed is 0, then this just becomes the square root of 1, and so E is just equal to mc squared. In other words, having mass means that you have energy. Those two are equivalent. It also means we can get the kinetic energy, any additional energy of moving, of not being at rest, by taking the total energy and subtracting out our rest energy. So writing it as mc squared divided by the square root of 1 minus v squared over c squared minus mc squared. That will tell us how fast something is moving. All right, let's look at an example. This example 8, the sun is losing mass. The sun radiates electromagnetic energy at a rate of 3.92 times 10 to the 26 watts. What is the change in the sun's mass during each second that is radiating energy? What fraction of the sun's mass is lost during a human lifetime of 75 years? Interesting. So we're going to first note this rate, right? 3.92 times 10 to the 26 watts. The watts is an important clue. What does that tell us? Well, remember, watts are units of power, of energy over time. So this is telling us the energy per second. So we're already in really good shape because we're trying to find the change in sun's mass per second. We know the energy per second, so we just need to convert that energy into mass. That's where our E equals mc squared is going to come into play. Or more specifically, we can describe it as the change in energy, delta E of the rest energy, is equal to the change in mass, delta M, times c squared. And here we're interested in knowing how the mass changes, so we're going to divide both sides by the c squared to get this equation for the change in mass is equal to the change in rest energy divided by c squared. So we have our 3.92 times 10 to the 26 watts, remember, are just joules per second, so they've converted that to joules per second. We're only interested in 1 second here, so we can multiply by 1 second. We could also leave it as a rate and get kilograms per second if we just didn't multiply by 1 second here. And then we're dividing by our speed of light, 3.0 times 10 to the 8 meters per second. And then squaring that. So make sure you square it so that you can get the math right here. And so joules, get the seconds cancel out, the joules, the meters squareds divide out, the seconds squareds divide out, and all that's left are units of kilograms, mass. And this tells us every second the sun loses 4.36 times 10 to the 9 kilograms. That's a ton of mass. It's more than a ton of mass, right? That's an absurd amount of mass. Fortunately, the sun has plenty of mass to spare. So it's okay that as it gives off energy in the form of light, that it's losing some mass there. But we can look at how much mass the sun, the fraction of mass that's lost relative to the total sun in 75 years. And this will confirm that we don't need to worry about our sun dying on us immediately, right? So we get our change in mass. So 4.36 times 10 to the 9, this is the one we just had, taking that number and putting it over here, but making it now a rate, right, per second. So just taking out this, multiplying by 1 second, and this would leave us with something that's kilograms per second. So that's how we get to that number. And then we note, okay, we want to do it for 75 years, but years don't cancel seconds. We need a conversion factor. And it turns out there's 3.16 times 10 to the 7 seconds in 1 year. So that can cancel out our seconds, and then our years can cancel, and also our kilograms will even divide out. Right? And so notice all our units disappear. Why? Well, that's because we're just looking at a ratio. We're just dividing it out. But we end up with 5.19 times 10 to the negative 12. So the fraction of mass that the sun loses in your entire lifetime is 5 times 10 to the negative 12. It's minuscule. I don't think I could even detect that, right? It's a crazy tiny amount, and that's because the sun is super massive. 1.99 times 10 to the 30 kilograms. So we don't need to worry about our sun giving up all its mass, but this highlights how if something is changing energy, it is also going to be changing its mass. So let's check this out with a conceptual example. When is a massless spring not massless? The spring is initially unstrained and assumed to be massless. Suppose the string is either stretched or compressed. What is the mass of the spring after it is stretched or compressed? So A says is greater than 0 by an amount that is larger when the spring is stretched. B says it's greater than 0 by an amount that's larger when the spring is compressed, when it's shortened, which is shown in part the lowest figure. C says the mass of the spring is greater than 0 by an amount that's the same when the spring is either stretched or compressed. Or D, it remains 0. If it didn't have mass to start, it's not going to have mass when you just start stretching or compressing it. So I want you to think about this. So go ahead and hit pause now so you can reflect and come up with an answer. Did you do it? Right. Well, the key here is knowing that when you stretch or compress a spring, you're giving it potential energy. And the potential energy that you give it, you may have previously learned, is equal to 1/2 k, the spring constant, times x squared. If you haven't seen it, this is okay. This is just to illustrate a principle. You could do the same thing with a skateboarder on a ramp, and that would get you the same idea. So because it's x squared, it doesn't matter if the spring is stretched or compressed, it will have a change in energy, right? Anytime we have a change in x, that means we're going to have a change in potential energy, which is going to also then be a change in energy. If we have a change in energy based on E equals mc squared, we know we must have a change in mass that will be exactly proportional to that change in energy. And so we see that the answer here is in fact C. It doesn't matter if you stretch it or compress it. If you add energy to the spring, you're also adding mass. One of those strange but true things. All right, one last thing for this section is there's a relationship between the total energy and the momentum. If with our momentum equation, we saw momentum was equal to mv divided by the square root. So if we instead divide the v to the other side, then we start getting something that looks somewhat similar to our energy, right? We could imagine multiplying both sides of this by c squared, which as long as you do it to both, that's fair. And so we can ultimately arrive at this relationship that's really useful. And you don't need to worry about how you get there as long as you're comfortable with this equation, that the total energy is E, and that total energy squared is equal to the momentum squared times c squared plus the mass squared times c to the 4th, right? Where this second term is the rest energy, and the middle one is the momentum. So the other way you could write it is in terms of the rest energy squared, or mc squared, but when you square both terms of that, it becomes m squared times c to the 4th. And so this gives us a way that a lot of times with high-speed things like electrons, they won't specify how fast they're going in terms of velocity. They'll specify something like the momentum. And then based on the momentum and the rest energy, you can figure out the total energy. Or if you know the total energy, you can figure out the momentum based upon the rest energy of the electron. So that pulls us through section 28.6, the equivalence of mass and energy.